pleasure to be here at the second of these localization workshops. It's pretty clear from the keynote through the first couple of speakers, localization is intensely hot. So that's great news. I guess if there's any bad news, we're going to have to start having it every 6 months or every quarter with all the activity going on. But it's not just the location piece. There have been a lot of changes in the last several years. It's also the network and technologies. So I thought it would be worth talking about what's happened on the air interfaces, 2G, 3G, 4G. We've got all kinds of frequency bands. We've got the older control plane stuff, user plane, proprietary sorts of things, new technologies like the question that Byron just asked about femtocells and home node beams. All of that is going on in the wireless networks. How do we leverage that for location to make location better? There's a whole range of demands. I think Jalal really brought home the importance of extreme performance and safety of life kind of applications. I'm going to come at this sort of mashup of how do we meld these together from safety of life, mission critical, from those sorts of application perspective. Maybe not quite as extreme as Jalal started with, but what sort of performance do we need? How do we meld these together in a way that's useful for those applications? Just a brief background on Polaris for those of you who are not familiar with this. Polaris is a location technology company. That's all that we do is wireless location, primarily software-based location approaches. And again, coming at it from the E911 emergency call scenarios as well as law enforcement kind of applications. You could call it lawful interception, although delivery location is not intercepting anything. So we have a number of E911 deployments in the US and law enforcement deployments in Asia and the Middle East. So that'll be our perspective on things. Next slide. As Dick Lynch started out very accurately describing how did location get started, it really was driven by the E911 mandate in the US. And back then, the choices were simpler for location. The networks were simpler. It was handset-based or network-based. You were GPS or you were network-based. A little bit of picking and choosing which one. There was really one customer, maybe two. There's the FCC driving very strict performance requirements, and then there were the public safety. Public safety were the users, the consumers of the system. Obviously, that was long ago, starting with the emergency call application. Now we do have more, what Dick was talking about, a whole ecosystem that requires many different applications, many different vendors, many different consumers, the way they use the system. And so we have a whole range of safety of life applications, personal security, first responder. As I said, I think Jalal's requirements may be off the scale of some of the E911 kind of category of requirements. But there are a whole range of middle ground, sort of mission critical kind of applications that are showing up from enterprise and asset tracking, some of the healthcare stuff that Dick talked about, some of the law enforcement kind of applications might fall in that category, also safety of life. And there's consumer best effort, some of the location-based services. If you're doing mass location for marketing, maybe you don't have as strict a quality of service requirements. So the question as we move forward is how do we address these range of applications? What's the right mix of technologies to apply? Because it's not, it doesn't make sense to trigger everything that you've got on the device to go do some best effort kind of location, but for safety of life, it definitely does. So what's changed over the last few years? A lot of things. I mean, everybody knows about smartphones. We're all carrying them. Actually, it's not as relevant that we in this room carry them. What's really relevant to me is that my daughter wants one. I don't know what she wants it for, but she wants a smartphone. It's a consumer device. One of my colleagues at work said his daughter bought a BlackBerry. She doesn't even turn on the email service. She just wants a smartphone. So people are using and buying these smartphones because they're cool. So we all know that. the chips and capabilities in the smartphones, more and more technologies. Obviously, GPS is kind of a given these days in phone. Wi-Fi, Bluetooth, sensors are starting to show up. Compasses, altimeters will be there, gyros, accelerometers, those sorts of things. So those definitely play a significant role in the location capabilities that we can bring to bear. The networks themselves, 2G, 3G, moving into 4G, new frequency bands. Some of those networks are on new bands. They provide the networks. On one hand, you can look at it as getting more complex. On the other hand, from a location point of view, you can look at them as getting richer. There's more sources of information that you can use to refine location, particularly for the demanding applications. Femtocells and DAS are driving coverage more and more indoors, presents some very significant opportunities for improving location performance, doing the Z coordinate, altitude, those sorts of things. And then the whole application space, I realize you can't read what's on that diagram. It's really just meant to show the hockey stick that you've already seen in a couple of diagrams, that we've gone through that disillusionment period, and location is taking off in a big way. The older control plane, 911 was how we started. Supple, secure user plane location coming into play for more and more location-based services, consumer applications. Still some proprietary stuff out there. I would agree with Dick Lynch's comments earlier that we need to move more towards the standardized kind of approaches, so the application vendors know what they need to build to and larger market. So that's the networks. A rich set of technologies and bands and air interfaces at play. What's the problem? It's important to talk about that in the beginning. Outdoor location, many technologies can do that. Wi-Fi does a great job, we just saw that. GPS does a fantastic job at outdoors. I wouldn't say that outdoors is completely solved, but it's well in hand. We've done a great job as an industry of getting to that point. And even indoor itself, there are a number of technologies that cover some degree of indoor. Periphery of buildings, you can get GPS signals, you can map the Wi-Fi that's on the periphery of the building, you can do some degree of indoor location. I think the biggest challenge area is deep indoor, where it's hard to map things from outside of the building, but that's where a lot of users are, it's where a lot of emergency, safety of life, mission critical kind of applications are. How do we drive deeper and deeper indoors with better and better location performance? Not just accuracy, but time to fix, battery consumption, some of the issues that were brought up earlier. So that's, when you look at how we blend these technologies together, I'm kind of looking at it from that sort of indoor perspective. I don't think there would be a whole lot of argument in the room against the solution being hybrid systems. Dick Lynch started out with talking about there's no one technology that does everything. GPS is the foundation of all of this, though. I think it's very clear that the service providers, the handsets, the chips, GPS is there to essentially solve the navigation and outdoor problem. But there are some areas, the deep indoor, time to fix in some cases, battery consumption, maybe not for a lot of applications, certainly not for 911, but for some of the more pervasive kind of applications where you're pinning the handset very frequently, and you're doing geofencing. In Japan, they have a life log application where all the users are pinged periodically for their location, so they can tag it with what they're doing in their life. So those kind of applications can be battery hungry, and then some dense urban area challenges, but not particularly severe. So GPS is the base. Hybrid systems, you got to combine with something. Actually, I like Jalal's term cocktail, and better than hybrid. I think there's some better graphics to do with cocktails up here. But the real question with hybrid or cocktail is what do you blend it with? And my view on that, coming from the perspective that Polaris is that you would do that using signals of opportunity, cellular and Wi-Fi signals together, in an RF pattern matching kind of approach. So rather than plugging into some kind of a formula, you're going to build a prediction database of the environment for those signals. Take the measurements or signatures or fingerprints, whatever you want to call them, from those signals and do pattern matching of those to extract the best location performance, to drive things indoors, to be able to do fast time to fix, lower battery consumption, and some of the dense urban. I guess one other point here is I think most people in the room would probably agree that hybrid systems make sense. There'd be a lot of disagreement on what's a hybrid algorithm, what's the best way to blend these. I know some people look at it from the perspective of, well, just fire everything that the device can do and the network can do. Wait, if you've got a 5-second time for time to fix for an LBS application, or 30 seconds for 911, let your timer expire, and whatever you have, blend it together. Our viewpoint and my viewpoint is that there are much more intelligent ways to do that rather than firing off everything based on the quality of service requirements for the application, accuracy, time to fix, battery, how pervasive is the application. Trigger the right things. And some of the things that you can do is, for example, get an idea of whether you're indoors or deep indoors. Trigger only the right technologies that fit that usage scenario and that quality of service needs for the application. So those are the kind of hybrid algorithms that I'm talking about. Just one slide on pattern matching and why speculating or arguing that that's the right way to blend those the different signals of opportunity. Pattern matching, when you build a prediction database of the radio environment, has a lot of information in it. It has a lot of very site-specific kind of structure. It's able to capture some of the shadowing and non-line of sight effects. Obviously, you can't capture everything about the environment, but a lot of those built in. And you can, to a certain extent, model indoor and outdoor, predict whether users are indoor, do the right kind of things with hybrid based on that. And that information is very integral to optimal location determination. You're throwing a lot away if you don't use that. And I just put a couple of examples of this is from New York, Manhattan area, signal strength and time delay kind of maps, just to show that there's a lot of features, roads, building effects, shadowing, corner kind of effects, some similar sorts of things with time delay or very small scales. That information can be brought to bear for improving location performance. And what I mean by blending things together is, there are 2G, 3G networks out there. Sometimes they're making measurements for other location technologies or other applications like mobility management in the network. So whether it's AFLT in the CDMA networks or measurement reports in UMTS, those can be blended in a pattern matching approach. Moving forward to 4G, there are time difference of arrival, OTDOA, those type of methods being built into the standards. Those measurements can be used in a standard geometrical system of equations for time difference of arrival, or you can pattern match them and capture some of the structure to improve location performance. Wi-Fi can be put in that same context. Some of the things we're involved in at 3GPP standards are inter-radio access technology. So if you have a device that's got 2G, 3G, 4G, those networks may be different frequencies, maybe different topology, pull in information from all of those different networks. Next few slides just talking about how do we see cellular versus Wi-Fi signals, how do they come to play for improving location performance, particularly the indoor and deep indoor scenarios. So this is some testing, as I said, to be data-driven about the decisions, how do we use the different signals. These are from San Francisco testing wireless location signatures as our pattern matching approach, and then also Wi-Fi. This is some data from indoor, deep indoor kind of scenarios where the signals, the access points, the cells were mapped from outdoor kind of measurements, so no measurement inside of the building. So a typical kind of application where you're driving or more driving, in the case of Wi-Fi, for example, get the access point information. And what you see on here is the blue curve is Wi-Fi location estimates. When Wi-Fi gets a fix, when it's mapped access points, the accuracy generally is very, very good. So if you're on the periphery of the building or outdoors, it can be absolutely stellar. But as you get deeper into the building, you run into a yield problem. That, you start to see access points that you couldn't map from outside the building. So you have some some holes where Wi-Fi alone, you can't get a location fix. So in some of the testing in San Francisco, we see sort of 40% of those indoor, deep indoor kind of locations, you can't get a fix with Wi-Fi alone. So that's what the blue curve is kind of showing, that you can do well for some of the locations, but not all. If you use the cellular signals alone in a pattern matching approach, you get the red curve. So it covers pretty well indoors. 67% is about 50 meters, 52 meter kind of performance. So not at the 1 meter, 3 meter, 6 meter, but a very good performance in terms of E911 kind of requirements these days. And then it's all of our task, everybody in the room working on the technology to drive things up and to the left. That's better performance. So if you blend in a pattern matching approach, Wi-Fi and cellular signals in these kind of indoor scenarios, you're moving up and to the left. And these curves shift around. If you were to do outdoor, they shift around a bit. There's in some scenarios there's much more benefit to the blending, but in general we would see adding more and more of these signals to improve performance. One of the challenges with Wi-Fi and how you apply it to safety of life, mission critical kind of applications is, like it or not, it is an unplanned, unmanaged, unlicensed band kind of network. It's incredibly prolific. It's very successful. It works incredibly well. But relying on it for those sorts of mission critical kind of applications, you have to think about how you're going to handle the dynamic aspects of it and some of the unpredictability. And then also, even though Wi-Fi usually works, it's in an unlicensed band. There's some potential for interference. If you're thinking of safety of life kind of applications. So just a few data points that we've collected. We've done some Wi-Fi surveys along with some of the trials and testing that we've done. And a little over a 1 year period, we see about 60% commonality in the Wi-Fi access point database from doing outdoor kind of measurements of where the access points are. But then there's 40% change. Some of that, if you look over to the right, some of that is growth in Wi-Fi, which is good. I mean, potentially you remap that and you can improve accuracy. But some of it is things that have gone away. Some of it is things that have moved. And there's kind of more and more of a potential issue with mobile access points with mobile hotspots and smartphones now having the Wi-Fi access point capability. So there's going to be more and more of that dynamic nature. And then just one slide, interference, like I said, more for mission critical safety of life kind of applications. But it is in the band with microwave ovens, and I guess I should probably check the radiation levels of my house. But when I turn on my microwave oven, the Wi-Fi network speed goes down. So there is some interaction. So just some things that we've been looking at how we blend Wi-Fi. So how does that all distill down? And can you rely on Wi-Fi alone? Where do you need to blend in some other things? This is from some of that San Francisco testing that I showed before, looking at the location default rate. What percent of the time are you not able to get a Wi-Fi fix alone, versus the time from when you did the mapping. So if you did the mapping at time 0, 1 month later, what you see is outdoors, the lighter blue curve, you're 98% of the time you're getting a Wi-Fi fix, so very, very good. And then 6 months, maybe you're 10% kind of thing. Maybe some of the stuff Ted talked about with crowdsourcing, those kind of things, you could probably infer some of the new access points that are showing up and drive down this outdoor default rate to keep it fairly low, depending on how often you're willing to go redrive. Where I think there's more of a challenge is indoor. You start out with something like a 40% default rate from the testing that we had, and then you have 6 months, it's sort of 50%. So as you're going deeper indoors, you're seeing more and more of the unmapped access points and more and more showing up. That I think is a harder problem to solve with crowdsourcing, and even if you can identify some of these, there's some errors that propagate as you try and figure out these things are coming deep indoors. One of the other things that we've looked at and we see as a challenge in terms of Wi-Fi for mission critical safety of life applications as you get indoors is that the detection range. We're all familiar with laptops, and you turn on your laptop in any building, you're going to see some access points, and probably very many. The detection radius that we see, this is from some of that San Francisco and some testing at Stanford campus, is the detection radius for a couple of different models of laptops are shown in red, and then a couple of different models of handsets that have Wi-Fi built in. And so far we tested a small handful, but we see pretty consistent kind of performance. That there is a sort of a shrinking of the detection radius when you put Wi-Fi in a handset. Now maybe that'll get better as the antennas and power management algorithms, those kind of things mature. But there is a significant difference, about 2 to 1 is what we've seen, or even a little bit more than that. So you don't always see the same richness of access points deep indoors with handsets that you do with laptops. So last slide. What does all that mean? You put all those together with aging of the database, sensitivity of the handsets, and from what we see, there is Wi-Fi alone, is going to have some dead zones indoors where you're not going to be able to use Wi-Fi. And maybe you can blend with cellular networks, you can do other things, but Wi-Fi alone doesn't sort of solve the indoor problem. That was one of the questions that we had. Certainly, this first histogram up here shows that indoors you measure a lot of access points, no question about it. But then when you look at, okay, what are the ones that are in the database that you could sort of reverse engineer the location of or you can see from outdoors, then things start to shift to much lower numbers of mapped access points. And just kind of as an example of that, some work that we did on the Stanford campus, doing not just driving but also walking around some of the buildings there, and then looking inside. What do you see? Which access points can you measure? And this is one particular example. It's the library, actually, where you can see, there's an access point that's indoors, but there's a lot of signal attenuation blockage. You just don't see that from walking around the building, right outside the building, outdoors. So there is this sort of unmapped access point problem that needs to be solved. Our view on that is, Wi-Fi adds a tremendous amount, blended in a hybrid or cocktail combination, if you will, with the right algorithms with GPS to improve location performance for mission critical safety of life perspective. So that's it for thank you.
I think we're bumping up on the session break here, so why don't we end it there, and if you have any questions for Mark, just seek him out. I think we'll go to break.